What was your name again, so I can get you in the attendance?
Cecilia.
Aha. Yeah, really, really horrifically bad with names.
I prefer to be called Ceci, but I mean,
All right. I'll keep it
Easier?
in mind. Yeah. Nothing wrong with that. In theory, my name is Benjamin. I don't think I've ever asked that to be called by that ever. So, you know. Hey, hey.
Good afternoon.
Hello, hello. Welcome to the party.
Well, thanks for the invite.
Anytime, anytime.
Is it just us?
Got a couple people in here.
Oh, okay, cool.
Whoa, Robert.
Gotta slow down there.
Oh, come on. I'd like to go fast.
No, I don't go that way, but a meal's a meal.
$20 is $20, right?
Exactly. Yeah. Stay off my profile on Fiverr.
Good afternoon, Ben.
Hey, hey.
What's up, buddy?
Oh, just always excited about 2.5 hours of math, just like everyone else.
I'm super excited for 2.5 hours of math also.
Can I ask you guys to tone down the excitement? Okay.
Yes.
It's not
I'll
fair to
tone
the
it
rest
down
of
a
us.
I want a nappy nap and I want my binky. And, I don't know, some chicken nuggets maybe. Just
Or
pull
some
on
pretzel
revert,
pizza.
just give up.
Chicken nuggets sound pretty wonderful.
Depends on where.
So I had those KFC chicken nuggets,
I'm sorry.
bro.
Those are the tiniest things you've ever eaten, huh?
I've put bigger stuff in my mouth before.
I believe that. Yeah, their freaking nuggets are so small that like the dino nuggies you buy for kids are like 3 times the size. Like it's messed up.
What are we learning here?
Well, the really bad way to multiply, I guess. Slowly but surely, people trickle in. Give it another couple of minutes.
Well, isn't this the time that you said that people start dropping your class?
Yeah, yeah,
They just drop.
yeah. It just disappeared. I've had some people in my class for like, two seasons in a row, and just never seen them before. They're enrolled, never met them. But to be fair, you guys are actually the class that I've had that interacts with me the most. Like literally nobody has ever like asked questions. I just come in here, start talking, everybody's silent for hours, and then just like you'd see them checked out.
That's
So
boring.
when you go viral and famous, you're gonna remember that, right? You remember all of us.
I'm likely to if I ever get attention on a national scale, I'm going to retreat to a cave. Like, yeah.
I'll represent you. Don't trip. I got you.
Oh my God. It's like when I went to our we had a graduation for people who, went through the program. And I went and I didn't realize that they'd have every single person to work there to just stand up and say hello in front of everybody. And I'm like, oh God, I just full on, like everybody started clapping and I just stand up and I'm like, I hate this. I just said that. I don't.
Like an actual graduation or like just a graduation for like completing the.
Well, they actually tried to make like as nice of a graduation as possible. So took the
Oh, salami.
like banquet room or whatever the heck it is up there. And
I've been here, I've tried it. I've been here with an uncle and he graduated,
yeah,
but I didn't, but I still went and saw him. And it was pretty much everybody that was there,
yeah,
working there, and then everybody that was there.
yeah, and ridiculous amount of family. Like,
Yeah.
yeah. I guess the one I went to was comprised of people who didn't get to have one during COVID. and the people who, so it was a couple of years worth of people graduating who showed up for it. It was both cool and horrifying.
I like it. My son graduated from 8th grade and I got to roll up with him, pick up his diploma
Yeah,
in one of my buddy's cars. And pretty cool experience.
yeah. I mean, I always thought it was kind of silly once they started graduating from like every single school. And then I'm like, well, you know what? Maybe, if it gives them a sense of accomplishment and pushes them to do more, yeah, hell yeah. I'm down for that. Just, I don't want to go to one ever again. I don't want to stand, just pretend I'm not there. Everything broke out into discussions. I immediately like magnetized myself to the wall,
Not even if I invite you.
I will go full awkward. I am the guy who shows up at a party, hangs out in the corner and talks to the dog. All right.
It's all right. You got like 2 to pick from.
Yeah, coworkers like, you have to come to my house for like my uncle's marriage or something. And I'm like, that sounds horrible. And she's like, I got 14 dogs. I'm like, I get it. I get it. Okay, well, I feel like this isn't gonna fill out too much until a lot of people have emailed me and told me that they have obligations up until like 6:30 every time. So that's why it starts filling up a little later too. So, yeah, let's just start doing stuff. Oddly topical meme that I have here, you making plans in the group chat knowing I'm not gonna show up anyway.
He looks like he's gonna rape someone.
I'm recording this and putting it on YouTube, right?
I did not.
Yeah.
His face, like, wow.
When he said that, I was like, oh shit.
Well, the first part of it is gonna catch some attention.
Well,
He can put bigger stuff in his mouth.
I love bloopers.
The convenient thing is, I have it up there in case you guys need to go and review it. I don't think I've ever gotten anything on there in like 2 years that had more like 3 views. I think I was among them, so. Yeah, it's up there for no reason, really.
I checked it out. I thought it was updated, but I didn't see nothing updated. So
I am really bad about it.
Yeah. So I was like, all right.
I'm better about it when people tell me they use it. That has happened once. So, yeah, one time I just gave up on it and somebody was like, oh yeah, I'll use that. That's great. Okay, I guess I'll do it again. Been doing it again. Don't know if it's gonna get used, whatever. But yeah, the first 2 classes are on there already right now.
Okay.
Should be, better be,
Like,
but they're on there. All right, so today we're gonna do fraction-y stuff. Ratios, unit rates, proportion, literally all of that is fractions. Everything's fractions, just more fractions today. I know you guys love them. I figured we'd do more. You excited?
yeah,
Say you're
Yeah.
excited.
I am.
Okay. I'm the boss of all of you. You're all excited. All right. So
If you got shortcuts, and that's what they them do.
if I have shortcuts, you're all going to learn them. That is, yeah, I've said it before. I don't like how math is taught half the time. It doesn't need to be as complicated as it is. If there's an easy way, you're gonna learn the easy way. All right, so review stuff. There's not a whole lot of review stuff because everything's gonna be fractions anyway. So I'm literally just got some concepts and then going straight back into more fraction stuff. So reviewing fractions. We have proper fractions, mixed fraction, and improper fractions. Proper are the ones where the top number is smaller than the bottom number. Improper fractions are the other way around, top number is bigger. And mixed fractions are basically a proper fraction hanging out with an integer. So you got a number, you got a fraction, 1.5, whoop-de-doo. If you have something weird like a number with an improper fraction, then I don't even know what you'd call that. It's just a thing. It'd be a mixed improper fraction or something like that, like 5 and 15 fourths. That'd be weird. Never seen it? suppose it could exist.
What would you do with it?
Probably get it out of that messy format, honestly. That's really it. Like do the whole convert to everything to improper and call it good. Yeah, because there'd be no reason for that to be a thing. And hey, look, Ben's been playing with an equation editor. Hopefully it works out. We'll see. This is an image. If I hit enter anywhere on this page, it will jump around like crazy. So I can't get away with just, you know, editing in the middle of class like I usually do. But converting back and forth to improper and mixed. So if you have an improper like 13/7, you're converting that to a mixed fraction. You say how many times does the 7 go into the 13? Once, has a remainder of 6. So you take that 1 and you keep the 6 inside of the fraction. So 1 6/7. When you go the other way around, remember that was the one I had the shortcut. You take the number outside, multiply it by the bottom number, so 1 times 7, and then add it to whatever was already up there. So 1 times 7 plus 6 is 13, and you just put it over the same denominator and call it good. That's my favorite shortcut.
It doesn't seem like a shortcut.
You can do it a long way if you want to. Long way is putting a, huh?
It's just all long.
That's fair, but it's a lot longer if you do it the other way around. Plus, to be fair, that you know, get the annotates.
So, okay, I have a question.
I have an answer.
Okay, so are we just gonna have to show our work all the time? When it comes like on the GED or something like that, like we're gonna have to show them how we got that answer right. We can't just go like, oh yeah, we know it's this.
I think for the most part, it's going to be multiple choice, so there is going to be an element of chance in there. I'm not going to lie. You're probably not going to have to do a whole lot of showing work, but you're going to need to know how to do the work anyway. So if your notes are a horrible scribbled mess, nobody's going to care. So like this part down here in the middle, that's just me showing you what you would do. For the most part, you're just going to go right from here straight to there. This part is basically happening in your head. You don't have to write it down.
Okay.
Yeah.
But to show the work, you have to write it down.
I don't think I would show that, honestly. I really don't. There's a level of quote unquote showing your work that's drilled into your head in like elementary school and middle school and high school that I think is bad for you. After a certain point, when you're getting better at math, there's certain things you know how to do in your head and you can do them in your head. And if a teacher's like, no, you have to show your work, I can't tell you that you know how to do that. If it's something that everyone knows how to do in their head by that point, shut up and let them do it in their head. You know, that's unnecessary. You know, write down what you need to write down. Keep it like each step is there for you to keep what you're doing straight. As long as you're doing that and you're keeping it straight, and a lot of the showing your work is honestly, it's for you to be able to understand, hey, this is what I'm doing right now. I'm going down here. Going back and looking over your notes, you can see what you did. If that's not even a thing that you're going to worry about in the future, then you don't need to write it. Whoop-de-doo. I'm like, you should have seen the scribbled mess that I used to turn in. Like, I would show work, but not all of it. I've gotten to the point where I don't skip steps as much as I used to, just because I've been tutoring for significantly longer than I was taking the math classes. So that's, you know, on this particular slide, chances are everything hanging out in the middle of the equal signs on both the top one and the bottom one, you're not going to write it down. You're just going to go straight to it. Now, the long way, if you decided to hate your life, the long way on the top one would be doing long division. And the long way on the bottom would be to put a plus between the 1 and the 6/7 and combine them as fractions. And I don't like either of those ideas, and neither do you. So let's not do that. Okay, so speaking of useful things I was alerted today that I did not remember to mention is cross canceling. So cross canceling is, I don't remember if I explicitly mentioned it or not. So I'm just throwing some slides on here. But basically, last time we had fractions, we know how to reduce them by saying, oh yeah, this goes into the top, this goes into the bottom. Well, when you're multiplying and dividing numbers, you can actually take that a little bit further. Specifically, when you get to the step of multiplying them, any factors that are on top or bottom of either of the fractions, or if you're multiplying more than any of the fractions, you can cancel something out of the top and the bottom anywhere. And the reason for that is because if you multiply straight across, all those factors are going together anyway. And if the factors go together anyway, then you can reduce them now or you can reduce them later. So let's do it now before we get bigger numbers. So just a nice way of keeping things simpler. So for example, the example that I actually went over earlier. So you have 7/8 divided by 3/4. You'd have to change that to multiplication to divide fractions, because again, you hate dividing fractions. So you flip the second one upside down and change it to multiplication. Welcome to the party. Gonna write that you're here. Now I remember why I started doing the sign-in sheet. So I don't have to pull this out and type things. Okay, so you're at the point where we have 7/8 times 4/3. You can actually reduce right there. Normally you'd multiply straight across, but the 4 in the upper right can reduce with the 8 in the lower left. So 4 goes into itself once and into 8 twice, so you end up with 7/2 times 1/3. And then you can multiply across. So you get 7/6. Now, you don't have to do it that way all the time. You can just multiply straight across. Then you'd get 28/24, and then you'd have to reduce that. But the main benefit of this is being able to reduce with smaller numbers first, rather than waiting until you have bigger numbers and trying to reduce them. So it's useful. It's useful. Let's do a couple. Okay. So we got 12/10 divided by 3/2. Okay. So again, you don't want to divide fractions. So we're going to flip that second one upside down and change it to multiplication. And from here, you might be able to notice that, yeah, you could actually start off reducing this one anyway. 2 goes into both of those. But either way, they can still reduce with what's going on over here. Like if I decided to reduce them both by 2, I could say 2 goes into here 6 times and into here 5 times. But we could still do cross canceling by saying, hey, now we have a 6 there, but we still have a 3 here. That 3 can go into itself once and into that 6 twice. Now at this point, we have 2/5 times 2/1. Nothing else I can reduce, multiply straight across. And we get 4/5. Now, that's not to say you can't just multiply straight across right away and then reduce it later, but then you're having to deal with 24 out of 30. I'd rather reduce now rather than later. Right?
So if you were to try to reduce 24 from 30, it would just be like a whole thing. Right?
Well, 24/30, you'd have to look at that and say, well, what factor would they have in common? What's the biggest number that goes into both? And
6.
yeah, exactly, 6. So you'd be able to say, okay, 6 goes into there 4 times and 6 goes into there 5 times. You still end up with the same answer, but you're dealing with larger numbers that you might have to think about a little bit longer. So dealing with the smaller numbers.
I don't know, it seems easy peasy to me.
All right. I feel like making something horrible just as an example.
Isn't reducing just a simple division?
Yeah, basically. This is a terrible example. All right. Let's say we had 2/3 times 5/4 times 8/9 times 6/15 times 32/9.
Okay, I take it back.
If I multiply across on top, I get 15,360 over 14,580. I don't want to reduce that.
Yeah, no.
I don't want to.
Hey, but it's simple because you got the zeros at the end, which means it's some form of 2.
We got 0 at the end, which means that I could reduce it by 10 right away.
Yeah. And then
I
you got
could
the
do
6 and
2.
the 8. So that's 2s.
And then I do 2 as many times as I could. And then I do, but yeah, exactly. Like I could do that, but I would rather, not. I would
Okay,
rather
so
look.
what I meant to say was easy numbers like 24 and 30 is easy peasy.
When they're decent numbers, it's
Yeah.
all easy. That's the main thing that I'm trying to get through with this class is that everything scales up. These concepts will scale up. Is there necessarily a reason to deal with them at the moment? Maybe, maybe not. But, I could look at this and just be like, 1, 3, cool, all right. 1, 2, cool. 1, 2. What else we got? What else we got? How about this 2? Goes into itself once into here 16 times. What else we got? These are now 1 and 1, 1 and 1, so I don't care about those anymore. 8, 2, 16, 9, 3, and 9. There's a bunch of 2s over a bunch of 3s. That's as clean as it's gonna get. 8 times 2 times 16, 256 over 9 times 9 times 3, 243. Now, what the heck would the common denominator have been between those two numbers? 60. Apparently, both of these numbers were divisible by 60. I'm not gonna look at that and know that 60 goes into both of those. So that's where this method comes in handy, is it scales up. These concepts can go as high as they need to go and still work. That's the main thing of it.
So I have a question.
I have an answer.
You were reducing all those fractions,
Yeah,
and you weren't like going like the 5/4 and the 8/9. You went like 5/4 and the 6/15. How were you able to do that?
so the idea behind what it is we're doing, first of all, we have those commutative and associative properties to fall back on. Since everything is being multiplied together, it doesn't matter what order we do.
Okay, got it.
And another thing to cover actually is that you might have seen that 4 and that 8 first.
Yeah.
At which point that would have been a 1 and that would have been a 2. But if I had done that, I wouldn't have ended up reducing this guy to 16, so that would still be a 32, so it would still have that other 2 there. Doesn't matter how I reduce this or where, as long as I reduce everything as far as it's gonna go, I'm still gonna end up with the same pieces on top and the same pieces on the bottom.
Got it.
It all works out.
Thank you.
Yeah.
Now, this might be a stupid question,
But
but
I like those.
we don't have to convert the 22/10, right? Or the 45/11s.
To mixed fractions?
Yeah.
No. So what I usually drive home in these classes is that I truly hate working with mixed fractions. I hate them with a passion. Doing math with them is awful. And in fact, literally any math book you look at where you're doing math with mixed fractions says to convert it to improper fractions, do the math, and then convert them back. That is literally how you do math with mixed fractions. So, yeah, no. Unless something is explicitly requesting mixed fractions or makes better sense with mixed fractions, you are never going to see me use mixed fractions. In fact, after a certain point, other than word problems, after a certain point, you never see mixed fractions again, ever.
So it's only mixed fractions that we convert them into improper fractions.
Yeah, because I mean, if it's a proper fraction, you can't really mess with it. It just is.
All right, cool. I just needed that clarification. I'm sorry.
All good. Yeah, so this one, again, potentially would suck if I multiplied straight across. I guess I could have just gone to that one, whatever. But at which point, whatever giant thing you multiply straight across would have reduced by 55 over 55 on something like this. But I would rather say, hey, 11 goes into itself once and into 22 twice. 5 goes into 10 twice and into 45 9 times. So I end
we're
up with,
just always going across from each other, right, to see what goes into what?
yeah, so the idea is as long as the fractions are multiplied together, you can reduce anything on top with anything on the bottom. Yeah.
So would you still be able to do like only one part of it if you couldn't do the other part?
What do you mean?
Like the 10 and the 45, right? If you couldn't do anything with those, would you still be able to break down the 11 and the 2 and the 22?
Absolutely.
Like say the 45 was a 46.
Yeah.
You know what I mean?
If the 45 was a 46, I would probably knock a 2 into that and a 2 into that.
Oh, nah. Like a 43.
If they're prime numbers and I can't mess with them further, then yeah, I could still do whatever I want wherever I want. It'll still work out.
Okay.
Yeah. I mean, case in point, we go back to number one. I actually reduced with this 12 twice. This 2 didn't do anything. Like that one was just stuck there and it can be just stuck there. It doesn't matter.
Okay.
Yeah. And then with this one, you can reduce the 2's even further to 1s. So you end up with just the number 9. Now, a visual way of looking at this would be if I had broken everything down into their factors. 22 is 2 times 11. 10 is 2 times 5. 45 is 3 times 3 times 5. And 11 is, well, it's an 11. And if I'm multiplying these two fractions together, what I end up with on top is literally just going to be those guys multiplied together, and on bottom, it's just those guys multiplied together. So since it's all going to be in the same jumble and reduce eventually, then you can actually do it right away. And that's why that makes sense, is because the factors these break down to will all end up together on top, and these factors will all end up together on bottom. So it's kind of a shortcut in itself, because you're reducing before you could technically normally reduce. You're reducing what your answer would be, really. Don't overthink that. All right.
Tricks on top of tricks on top of tricks.
Word, homie. All right. So we got 5 over 28 divided by 30 over 49. So again, first thing you do is change it to multiplication, because you don't want to divide by fractions, because that's a painful concept.
Ooh.
Then we could break down. 5 goes into itself once and into 36 times. These two are divisible by 7. This is actually 7 times 4. This one's 7 times 7. So we end up with 1 times 7, 7 over 4 times 6, 24. And we can't reduce that any further. All right, do we like it? You might like it. Okay. Do I care to make you do 2 of them?
No, you don't.
I mean, I'm pretty sure it comes in the next set of problems anyway, so I'm leaning against no. But I did have to type those out and make it an image and copy and paste it.
Save it for the next class.
All right. Hey, look, I hate mixed fractions. Let's do a few slides on nothing but mixed fractions. Let's do this slide and 2 full slides of problems of mixed fractions. Yeah, it doesn't work as well when you got your flash on, right? Here's a picture of glare. All right. So as you can tell, it's easy enough to perform operations with basic proper fractions or improper fractions. But how do we work with mixed fractions? Well, as I said before, I hate it. The entire idea is you turn it into improper fractions, and then you do the math, and then you switch it back to proper fractions or mixed fractions. Now, the main reason you do that is because every mixed fraction is basically its own addition expression. It is 1 plus 2/3 in actuality, right? It's two different things put together. So if you're trying to do math with that, you'd have to embrace the distributive property like a psychopath. I could do it because I've done this for that long. But if I was in a class and they told me, hey, do this without converting, I would have hated my life. So don't do that. You could try it if you want to, you're feeling bold, but I wouldn't. So let's do a bunch of these. I love fractions. Don't you guys love fractions? Okay, well, you're going to. Or at the very least, you're going to hate them less. That's pretty much what I'm shooting for, is hating them less. I'm just going to write down one at a time. Look at that. Doesn't even show me on the participants window that there's more people when I have it this way, because I don't see the scroll bar. I realize a bunch of more people are in here. Look at that. All right. All right. All right. All right. We got people. All right. So we got this thing. We got to multiply 10 and 1/9 times 4.5. Now, bless you. Everybody gets one. All right. There's actually multiple ways of doing this, but it's horrible, and I'm not going to show you that. But again, you could hate your life with the distributive property on something like this, but you'd have to have pluses in between these and parentheses around them and do this whole distribution thing that you don't know how to do yet. And honestly, it's pointless, because the easy way to do it, you take the integer, multiply it by the bottom number, 10 times 9 is 90, add it to the top one. So we end up with 91/9. And we are multiplying that by 4 times 2 is 8. 8 plus 1 is 9. So we have 9/2. And hey, look, cross cancellation's coming in handy. 9 there and 9 there. Going straight across, we just end up with 91/2, which that's an odd number, so it's not going to divide. So there's that, but we do need to convert it back to a mixed fraction. So we say, how many times does 2 go into 90? So you go down to the next number it would go into, which would be, 90. And then you'd have that 1 left over. So you would end up with 45 1/2.
So that common denominator, or the denominator stays the same in this part always. Well, before you get the actual number.
As in this one to this one, yes. Yeah. Because all you're doing at this point is essentially just reducing out whatever would go in evenly. You have 91/2. Okay, how many holes is that? Well, 45 of them. Okay, what do you have left? 1 of them. Cool. So that's still 1/2. Guys, want to see something horrible? You want to see what happens if you had to multiply this normally without converting? No?
Yeah.
Just oddly nodding your head. A couple of people nod their head. All right, all right. Here's math you're not going to have to do for a while. This is why I hate mixed fractions, because if I had to work them on their own, I would have to multiply everything out separately. That would be you're curious about it, we're not gonna get to it for a while. Foiling binomials. That's what that is called in algebra. You normally don't need it until algebra because there's a nicer way of doing this, but you would then have to get a common denominator here. 40 plus 5 plus 8 18ths plus 1 18th, combine like terms, 45 plus 9 18ths, 45 plus 1/2, which is 45 and a half. I was tutoring a friend the other day and I was really hoping I had an opportunity to torture her with this, but it's a shame, really. So yeah, I like this way.
If you had to write that as a percentage, it would be 45.5, right?
I mean, that would be a decimal, not a percentage.
Oh,
Yeah. If it was a percentage, it would be 4,550%.
Hmm.
Yeah, let's do another. What's my next one? I got 2 1/3 plus 51 7/8. Now this one, I don't know that the shortcut I have for this would come in handy, but I'm going to show you 2 different ways of doing this. Because I don't honestly know how often you're going to do this, and that's why I say that. So we get it into just improper fractions. So 2 times 3 is 6 plus 1 is 7. So it's still over a 3. Plus, why did I choose 51? What is wrong with me? 51 times 8 is 408 plus 7 is 415. Still over 8. Oh my God, why did I do that? I have the feeling I typoed into the equation editor that I was using, but you know, we're too far along now. All right. I feel like that was supposed to be just a 5. Whatever. Whatever. We're dealing with big numbers. Okay, so we have to get a common denominator because we are adding fractions between 3 and 8. First time they, cross over would be 24. You multiply the numbers together at this point before you have a better way of doing it, or just kind of reason your way through it.
And this is just for adding fractions.
Adding and subtracting fractions, you must have a common denominator every time, no exceptions.
Hey, you can't do cross cancellation, can you?
No, cross cancellation only comes into play when you are multiplying. So it technically works if you're dividing as well, because it turns into multiplication, yes, but it only works when you are multiplying 2 fractions. So we have to get a common denominator, which in this case would be 24. So I have to multiply this one by 8 over 8. And this 415 isn't big enough yet, so we're going to multiply that by 3 over 3. Do not be intimidated by large numbers. They are just large numbers. You will be mostly throwing them at calculators. So just look at them as, yeah, that's a couple extra button presses.
Okay, wait, where'd you get the 3s from on that side again?
This guy?
Yeah.
Because we need to get the denominators to be the same. Okay. So the first time 3 and 8 would have a multiple that's in common would be 24. So we're going to multiply this one by 8 over 8 to get the bottom to be 24. We're going to multiply this one by 3 over 3 to get the bottom to be 24. And again, we are able to do this because this is an ugly 1 and this is an ugly 1, and you can multiply anything by 1. I always like to clarify on that because a lot of times I'll get the question, hey, I thought what you did to one side, you had to do the other. Why is there an exception here? Because that's a 1. If that wasn't a 1, then we would break what we're dealing with and we don't want to break it. Okay, so we end up with 56 over 24 plus 415 times 3. We get 1,245 over 24. Beautiful. What the heck is this? I don't know. I still have 1245 on my calculator, so I'm hitting plus 56. I get 1301. Good. Now we gotta figure out how to convert that back. That's why I'm thinking I did a typo. Let's see, what can I do to be cheap about this? Everybody's gonna have a calculator when they're doing tests. Okay, I have a cheap way of doing this. Suppose for the notes, I'll write down what I'm doing in a calculator off to the side. But if I do 1301 divided by 24, I get a decimal, right? Which doesn't immediately jump to our answer, right? Well, it might, I don't know. Depends on, ooh, okay, thank you, fraction decimal button. That didn't help. So this you might not see as it going in nicely, but what that's telling us is that it goes in 24 times and then some more. So if I figure out, I'm going to actually write this down just for note purposes. That's telling me that this thing goes in 54 times. So 54 times 24 is 1296. So that's how many goes in evenly. So if I figure out the difference, which in this case would just be 5, that would be that remainder. So what I've done is I've very cheaply used a calculator to reduce this, saying, hey, this goes in 54 times. And then we would have a remainder of 5. It's a little cheap, but it works. Now I do have a shortcut for this. Kind of a shortcut, not really a shortcut. For this problem, it's a great shortcut. It's not useful all the time. When you got something ugly and stupid like this, pretty useful. But shortcut wise, I'm going to take advantage of how mixed fractions actually are. I've told you multiple times that these are basically addition problems on their own, right? It's 2 plus a third. This is 51 plus 7/8. Well, if I put a plus between them all, now I can use those commutative associative properties. I can add these however I want. And you know what I'd like to add together first? The 2 and the 51. You know what I'd like to add together second? The 1/3 and the 7/8. So you can actually get away with getting a common denominator here. And dealing with a smaller set of numbers. You just end up with, well, you might end up with the exact situation that I told you could potentially happen earlier. Hey, look, we have an integer and an improper fraction together. We have a broken mixed fraction. How do I deal with that? Well, how many times does 24 go into 29? Once. Cool, we can add that to that 53. And then we would have 5 left over, right? I like that. I like that. And that's taking advantage of the fact that they're, you know, 2 separate numbers. And the properties that you used. You are never going to see this done this way in any math book. Literally ever. Nobody would do this. I will 100% do what I gotta do to make it not suck. I did not have to deal with 1301 over here. Now that could get trickier depending on signs. Like if there was a minus between the numbers originally, you'd have to distribute that to both of these, and this would have to have a minus on both of those, but it would still work. And if it works, I like it. Now, the main reason I'm saying you might not need to commit that shortcut to memory is just because it's not going to come up very often. Just this being useful really doesn't pop up too often. What's useful is sometimes being able to understand, hey, a mixed fraction is an addition problem. You might be able to make that work for you. You might not, whatever. Let's do more. You guys love fractions yet?
Hell yeah.
All right, I'll take it. All right. Taking advantage of those rules is the only way I would do number 3. Because normally, if I was to do these as fractions, I would have to convert this to an improper fraction. I'd have to convert this to a fraction, put it over 1. I have to get a common denominator between them. Add across, then reduce, right?
Oh, so it wouldn't be 7 2/5?
Oh, that's 100% what it is. What I'm telling you is there's an easy way to do these and a hard way to do these. Depends on the problem. In this particular case, we can see that the 3 doesn't have any weird fractions. So we can 100% get away with just adding it to that integer. No mess, no problems, right? Main thing I'm getting forward on that problem is don't make it harder than it needs to be. Speaking of harder than it needs to be. Look at that thing. Isn't it beautiful? How would we approach this?
It's division. So you would have to change it to multiplication, right?
Well, fractions are division, remember?
3 over 5 times. And you're just swapping the 2. And 15, right?
But that's the thing. If I was trying to convert this to multiplication, how would this flip upside down?
You have to convert the 2/15. The 2.
Yeah, you're not going to want to do that until after this is an improper fraction. So the first thing you're going to do is convert this to an improper fraction before you do the flip and multiply thing. So 2 times 15 is 30 plus 6. 36 15ths. Now we have something that we can work with, right?
Well, can you redo the cross multiplication? I mean the cross cancel.
I mean, once we're here. But you might have noticed something already. This already does reduce. Three goes into both of these, actually. 3 goes into here 5 times, and 3 goes into here 12 times. But this one's just gonna keep reducing like crazy, actually. This 5 can go into this 5, and this 3 can reduce with this 12. So I got nothing but 1s and a 4. 1 times 1, 1, 1 times 4, 4. How many times does 2 and 6/15 go into 3/5? Apparently a quarter of the time. Would that break your brain? Yeah, probably. I don't want to think about that. I don't want to try to visualize it. Sounds painful. Let's not. All right, are we enjoying this? Am I losing you guys yet? Hey, look. We have something to do alone. How do we feel about this? Is 6 minutes long enough?
Ish.
Ish. Getting some hard ishes. All right. Let's slap a 7 on there. So I'm going to try to shut up for about 7 minutes. It's gonna be hard for me as usual. Just start working these guys out. If you have questions, as usual, feel free to ask them. If you do not have questions, then do not ask the questions that you do not have. That kind of makes sense if you think about it. How's everybody doing? Not happy?
I got stuck on the second one.
Huh?
I got stuck on the second one.
Second one? Okay. Don't blame you. That one's probably the messiest one.
Just a quick question. You can reduce whenever whenever you can, right?
Yes, the only time you wouldn't want to reduce is when you're getting a common denominator to combine two fractions. Because that literally just is undoing what you just did, but normally I wouldn't go out of my way to say that, but I've seen a ton of people do it. It's actually a very common problem. You guys want more time or you want to go through? So that's what I drew together on my calculator. I don't know if anybody got those or not.
Dude, I don't know why I was doubting myself about the second one. I really don't, like, I had to use a calculator because like with the answers I got.
Mhm.
I'm like, just trying to divide it, but then I'm just like, okay, I don't think that's the answer.
Well, I will admit that getting it to work nicely on a calculator is not the nicest because again, mixed fractions kind of suck. So let's just run through them. So I feel like everybody had a problem with at least one of these guys. So 5 times 3.5. There's a couple of ways to do it. One way to do it would have been kind of imagining the plus there and distributing, because we could do 5 times 3, no problem. It's the 5 times a half that might throw you off a little bit, but the nice thing there is it'd be 5 halves, and you'd only have to reduce that part. Now, the other way to do it would be to do just straight fractions. That 5, we're just going to put over 1 for now. Over here, we're just going to convert this to an improper. So 3 times 2 is 6, plus 1 is 7. So that's 7 halves. We multiply straight across. So we have 35 over 2. Now from there, you need to know how many times 2 goes into 35. If you don't know it right off the top of your head, you can always go down to the next number that it would go in evenly, which would be 34. Punch it into a calculator if you want to. You could potentially just do 35 divided by 2 in a calculator. You get 17.5. So you would know that you'd have 1/2 left over. But either way, the 2 would go into there 17 times, and you would have 1 left over.
Where did you get the 7?
This thing,
Yeah.
do 3 times 2 plus 1.
Oh, okay.
Remember, you got to multiply these 2 together and then add in that direction.
Okay. Thank you.
Yeah. Let's see, what was number 2? That's 14 1/8 minus 4 5/7. So this one's kind of messy because of the numbers you end up with. So you'd want to convert these both to improper first. So 14 times 8. You get 112 from that. You add the 1 up top and you end up with 113. And then we have 4 times 7 is 28 plus 5 is 33. Then we got to get a common denominator. So 7 and 8 don't have anything in common, so chances are you just multiply them together, you get the common denominator between them. And that is the case in this one. The common denominator between them would be 56. So essentially, I'm just going to multiply this one by 7 over 7 and this one by 8 over 8. So both of the denominators are 7 times 8 now. Works out to the same number, whatever that would be, that would be good. Now, we don't have the nicest numbers from here. 7 times 113, you get 791 over 56 minus 33 times 8, 264 over 56. Not the prettiest numbers, but follows the same rules that we're used to. All we've done, we've converted them to proper fractions. We get a common denominator, and then we can do our subtraction across the top where they keep the same denominator on the bottom. 791 minus 264, get 527. Now we'd have to reduce these back to a mixed fraction. So we need to know how many times 56 goes into 527. Not exactly the nicest one, but I know that if it was 10 times, it would be 560, right? So probably 9. So if I go to my calculator, do 9 times 56, I get 504, which is just a bit below that. So we could say it was 9, and then if that was 504, we have 527 here, we would have 23 left over. How many of you got that one? Anybody get that one? Kind of?
I just cut to the fives when I said the word.
Oh, you got to this and you're like, got it.
Yeah.
Fair. And yeah, what you have a lot of different strategies you can go to, but the main thing with reducing these is that it doesn't come to you naturally until you've done it too many times and it just kind of flows better. Until then, it just, going through the motions. Like I said, one thing you could do, punch it in your calculator. You could see, oh, well, you can see the 9, but you don't know what to do with the rest of it, right? Well, you get to that point, you say, okay, well, it goes in 9 times. Well, what would that be? So you do 9 times the 56 to the 504. Then you can see, okay, well, that means 504 are going in. Whatever's left would be our remainder. So
Like you can't
do that.
reduce 23 over 56, right?
Nope.
Even though 3 goes into 6 twice.
What was that?
You really can't
What
reduce
goes
it?
into 23?
Gotcha.
Yeah, you're not worried about the ending numbers. That might give you, actually a lot of times that'll give you like a hint of what might go into them to reduce by. But nothing's really gonna go into the 23. So yeah, I can see where you were going with that, but you'd have to make sure something would go into the full number instead of just the last ones. It could be a hint, but not really a concrete. Okay. And we had 2 3/5 minus 1 3/7. Man, I wrote that terribly. My handwriting's never gonna get better. All right. And this one follows basically the same exact steps. We get the common or convert everything to improper fraction first. So 2 times 5 is 10, plus 3 is 13/5, minus 1 times 7 is 7, plus 3 is 10/7. This one has the I guess luxury of having nicer numbers. Doesn't end up necessarily too nice once we get a common denominator. Both of these numbers are prime, so I'm just gonna multiply by, whatever they're missing, 7 times 5, 7 times 5. That way we get a common denominator. Up top, I get, what is that, 91, I think? Yeah. 91 over 35 minus 50, 35. So we end up with 41 over 35. And that just goes in once with 6 left over. So out of the 3, that second one was kind of mean, huh? There. Now, the main difference between the ones that were doable and the one that wasn't, what would you say? What was the roadblock on this problem? What threw you guys off? Reducing more, bigger numbers, bigger stuff to deal with. Just uglier stuff here. All right. Yeah, so that is something that can come up sometimes, is that as these problems get harder, really, if you look at it, this problem took the exact same steps as this problem. Like you could even like take this, almost put it over this as an overlay and see the exact same steps. But yeah, the main problem there was dealing with these numbers and being able to work with them. So that's an important skill to have. And like I said, you kind of just got to get the feel for that after, you know, a bunch of problems, working them out, finding that groove of where that information comes from, because you might be able to say on paper, yeah, I know it's how many times this goes into that, but getting there is going to be tougher, right? So like I said before, you got your calculator handy. Worst case scenario, you throw it in there, your calculator says 9 and some change, just take that as it is. You know that it goes in 9 times. How do you work from there? Questions, comments, concerns? You ready for more fractions? Am I losing you guys yet? This is the one where our brains explode. See, this is why people drop this class. I told you. It happened. I start losing everybody, and then the next time I teach it, the next class, like 2, 3 people less. The next time there might be, you know, 1 more than that. Then it starts, you know, starts slowly dropping off. It happens. Hey, look, word problems. Didn't we want word problems the other day?
Yeah.
Cool.
Joseph was asking for him.
Well, notice that you don't see the word work these alone anywhere. We're gonna work them together. Does that sound like a plan? Cool. So word problems are just a natural progression of math. Math is literally stuff that we didn't necessarily make up. It's rules that we've kind of come to work out from the way things are. So the 2 things that I get asked the most in math are, when am I ever going to use this? And I also get told, hey, I hate word problems. And when are you going to use this? On the word problems. One is the answer to the other. So yeah, they're just applications. So these ones aren't too bad. So we have Linda walk 2 1/3 miles on her first day and 3 2/5 miles on the next day. How many miles did she walk in all? The main,
A lot.
huh?
Basically,
A little less, but yeah. I mean, yeah, and for the most part, you know, that's actually a useful skill right there. That's called estimation. That is legitimately math. Because if you did the math on this on paper and you got like 12, you'd be like, oh crap, something went wrong, right? Exactly. So you know how to make that make sense. That's actually a good skill. Now, is it exactly 6? No, so we got to do it. Is she gonna tell people it was 6? Oh yeah, she's gonna go over that. So obviously, if we're combining these two numbers, it's just going to be adding them, right? So we have 2 1/3 plus 3 2/5. Okay, the usual, get into an improper fraction. 2 times 3 is 6, plus 1 is 7, so we got 7/3, plus 3 times 5 is 15, plus 2, 17/5. We need a common denominator between 3 and 5, it'd be 15. So this one's gonna need a 5, multiply it by 5/5. This one's gonna need a 3, so multiply it by 3/3. We get 35/15 plus 51/15. So whatever our answer is gonna be in 15ths, we just add across on top. 35 and 51 gets us 86. Then we say, how many times does 15 go into 86? Well, 15 times 6 would have been 90, so I'm willing to bet it's 5. And let's see, 5 times 15 is 75, so we'd have 11 left over. So 5 and 11/15. Since it's a word problem, you always want to put your units there. Miles. It's like when you're a kid and they're making you do word problems and they tell you, oh, you have to write it in a complete sentence. I don't care if you write it in a complete sentence. You know what you're answering. I like the units on there though. I like to know what the heck it is I'm working with. 5 and 11/15. 5 and 11/15 1. Centimeters? Hope not. That's a really crappy run. What would be fun is converting that into feet. Don't worry. That's only going to be a week or 2 out.
I have a question.
I have an answer.
Okay, so why do you put 5/5 and 3/3?
Because in order to combine these two fractions, we need a common denominator. So they have to be over the same number. And between 3 and 5, the first multiple that they both have in common would be at 15. So if I multiply this one by 5/5, it'll get a 15 on the bottom. If I multiply this one by 3/3, it'll get a 15 on the bottom. So now we have that common denominator, we can add a cross on top, keep that 15 on the bottom.
Oh, okay.
Does that make sense?
Yep. Yeah, okay. Thank you.
Anytime.
Thank you.
All right. I don't want to do all these. We'll do the second one, move on. I got too many fractions, really. I wanted to be done with this by now. The class has done what, like 3.5, 4 hours of fractions so far? I'm done with fractions, it's Oreo. Okay, so it says, Gabe is barely 2 3/5 years old. He has spent 1/3 of his life sleeping or crying. I know the feeling. How much of his short life has Gabe spent either sleeping or crying in years? Also, why do people say sleep like a baby? Nobody sleeps like a baby. You sleep like a baby, you're sleeping for 20 minutes at a time and then waking up and screaming and crapping on yourself. I don't want to sleep like a baby. I want to sleep like I'm elderly with a narcolepsy problem. Just want to be dead to the world, man. And deaf. All right. So how do you find 1/3 of something? What operation are we doing? We have an H. I don't care that it's a complicated looking number to work with. But what operation's happening here? How do we find 1/3 of something? You got,
Divide.
huh?
Divide.
That's one way. That's one way. If you divided would you divide by a third?
Well, you can't divide, so you have to multiply.
What would you multiply by?
That's a good question. Very good.
You're on the right track. If you're trying to find a third of something, what do? Usually you just divide it by 3, right? Well, that's one way to do it. We could divide this number by 3. Generally, when you're looking for a fraction of something else, that's when multiplication comes in. How do I know on paper, if I have 60 bucks in my wallet, what's a third of that? I take the 1/3 and then multiply it by that 60. And I end up with the 20, which is significantly more money than I have. That sucker's empty. There's receipts in there. Be nice if there was a gift card or something. I don't know. All right. So that means we're going to do 1/3 times 2 3/5. Yay. Now, one thing I like to do is when I'm dealing with word problems, I'm going to say, okay, well, this is 1/3 times a time in years, right? So I'm just going to go ahead and write my units down here. Just there, randomly somewhere, doesn't matter where. Just so I can remember, hey, when I'm at the end of it, I can write down what it is I'm working with. Okay. So in order to do this multiplication, I'm going to want improper fractions. So 2 times 5 is 10, plus 3 is 13. So we have 13/5. We're going to multiply straight across. We get 13/15. That doesn't reduce. And also, it's a proper fraction. We haven't actually run into a proper fraction so far. But that's a proper fraction. So I don't have to convert it to a mixed fraction because it already kind of is. We're good. That's it.
So technically, how many years is that? Not even 1?
Not even 1. 13/15 of a year. You want to know how many days? Multiply that sucker by 365. What is that? Hell if I know. I'm going to throw it in a calculator. You would see this kid on a blanket on somebody's Facebook with the number 316 next to it. That's what he would do. And it'd be bright colors everywhere. And you'd look at their page and it'd be nauseating. Yeah, you know the type. We all know the type, right? My precious little angel is almost a year.
Did you look at my Facebook page?
Not often. All right. Yeah, I'm feeling good on that. You guys feeling good on that? I'm feeling good on that. Feel great on that. How's everybody's brain feeling right now?
Tired.
Tired? Those of you online, what's the verdict?
Tired.
Tired? Did I melt your brains a little?
A little, yeah.
Okay. I get that. All right, well. Let's take a break. Like an actual break, like just break.
Okay.
Let's say I've done this before in classes. I don't normally like to do it too often. But yeah, when your brain is goo, then we're gonna do that. So let's break until, I don't know, 7:30. Let's do 7:40. And yeah, just breathe. You know, hit the bathroom, hit the kitchen.
There's a kitchen here.
No, but people are online.
I was like, wait,
I mean, technically there is a kitchen, but it's for faculty, and also I've never actually been in there. I think it's actually Like, right over there. Yeah, I'm pretty sure it might actually be right on the other side. Just not going over there.
Yeah.
On back. Recording is on. Let's play some catch up. Let's get past all these fractions, right? We done with fractions? Like, we're not actually done with fractions. There's more fractions. Like, only a few more slides of fractions.
What's a few?
Huh?
What's a few?
Let's see, 1, 2, 3, 4, 5, 6, 7. 7 is a few. We're gonna skip a lot of that because I actually want to like get to other subjects. Okay. So literally the next 2 slides are concepts. Ratios. So a ratio is a comparison between 2 numbers. Every fraction is a ratio. It's written in a bunch of different ways. You can write 2 to 3 with a colon, 2 to 3, or as a fraction, 2 over 3. That's a ratio, every single one of them. Now, personally, the first couple options I always see as odds, like betting odds, you know? So I don't like to use the word 2 or the colon too much with ratios, because I like things, if you're writing in a certain way, I like it to mean one thing. So personally, I usually only use fractions. So for instance, here we have an example of how many different players there are in a soccer team. And it's asking what's the ratio of midfielders to the total number of players. It says you have 11 total players. It says 5 of them are midfielders. So you would do 5 over 11. That is the ratio of midfielders to players, right? That is pretty much it. That is the concept of ratio. Now, in terms of ratios, I find the most useful as unit rates. So that's what I'm going to be mainly aiming for on the problems for this is unit rates. They're very, very useful. It's like, yeah, like I have in here, if a tub is filling at a rate of 10 gallons every 2 minutes, then the unit rate is 5 gallons every 1 minute. A unit rate is comparing some amount of one thing to a single amount of another thing. Like your car gets however many miles per gallon. You're driving however many miles per hour. You're going 25 miles per hour. Guess how many miles you go in an hour? 25. If you're going 25 for 2 hours, it's going to scale up. You're at 50 miles, right? So that's the usefulness of unit rates. If you know what the unit rate is, it can work up to whatever you need it to be. I always like to use the example of shopping. And in fact, I have multiple of those problems for shopping. But for instance, if you're in like a Walmart, you look at the price labels, there's always a smaller amount in the corner in orange. And it's like, oh, it's this much per ounce. That's a unit rate. You can compare the unit rate on like one type of cereal versus another type of cereal, and you might see, hey, the bigger box is the cheaper by the ounce. Or like the other day when I was looking at it, and I was like, why is the one that's larger more expensive? It's cheaper to buy 2 of the small ones. And you know, it can save you money that way. Not even kidding, right? Like, what the hell? So that's their usefulness. So here we have a couple of problems. Number 1, a car travels 420 miles on 15 gallons of gas. Express this as a unit rate in miles per gallon. And essentially, what the hell am I hearing? Essentially, all you really do is either reduce fractions or break them down into decimals, preferably not too many decimals. But it can help you find unit rates that way. Because unit rates aren't always necessarily a fraction. They can also be decimals, like I said, in like dollars per ounce, something like that. So if we have 420 miles and 15 gallons, you would usually start off expressing this as a ratio between the gallons and miles and gallons. If you're looking for miles per gallon, you're going to do the miles on top and the gallons on bottom. Whatever the first part of that is going to be the top of the fraction. Now, at this point, all you really do is either reduce or divide. So I'm going to throw it in a calculator. 420 over 15, it goes in evenly to 28. Now, if it reduced, it would have reduced to something over 1, right? Just perfectly. 15 goes in there 28 times. So that would mean you would have 28 miles over 1 gallon now. That makes this miles per gallon. You know, and it makes sense, right? You were driving on a road trip or something, and you knew how much gas was in your tank, and you knew how far you drove on it. You could compute that pretty easily, right? That's pretty much the usefulness of these. Now for the second one, it's a little on the longer side, but it's actually very quick. So a spice company offers different prices depending on how many ounces of each spice a customer buys. Which of the following is the most affordable spice to buy per ounce? And this is something you might run into. You might not run into, 5 sizes of a spice for no good reason. But, the general idea is that you could kind of see where this would come in handy. So what I'm going to do, I'm just going to make it a table just because honestly, it's going to be easier to write that way. Helps if I actually write down the right number though. Okay. So we're essentially looking for which one has the best buy, right? So it kind of just made a table in ounces and dollars, just because honestly it was easier to write that way and I didn't have to write the dollar sign that many times. But if we're looking for cost per ounce, you would first kind of think of those units in a ratio. And you can see, okay, if I'm looking for cost per ounce, that's the same as dividing the cost by the ounces, right? So that's what I'm going to do, is I'm just going to go ahead and do the cost divided by the ounces. Now, I know we're dealing with dollar amounts, but I am going to go out to the third decimal place, just because that might actually be relevant at this point. All right, so we have, all of these are in cost per ounce, right? So if you're looking for the best purchase, it's going to be the lowest amount. And this last one has 0.09 cents per ounce. The next one up is this one that was 0.098, which is really close to going up, right? And in fact, since all of these would actually be in dollar amounts, chances are that would round up to 10 cents, right? So this would be the best purchase because it is the lowest unit rate. Does that make sense? Cool. I feel like everybody's brains are off right now.
But wouldn't C be a better purchase? Because you got 5 ounces more and it's only 40 cents. Not 40 cents. It's like, you know, it's not that much more.
68 cents. So it's not much more. So I mean, really, you go to the store, if you really need that at 5 extra ounces, yeah, you're probably gonna end up buying that. None of these are particularly horrible, right? But you know, at the end of the day, this one would be the best purchase in terms of value. This one you're paying 9 cents for every ounce. This one you're paying 9.8 cents for every ounce. So by the ounce, this one is a little bit more expensive. But like I said, you know, it just depends. It's a situational thing.
Excuse me, I have a question.
I have an answer.
So what you did in your use multiplication? What's
I did division, cost divided by ounce.
Oh,
So what I did was I
okay.
did 275 divided by 22. That gave me this guy. Same thing all the way down.
Okay, the price for the amount.
Exactly. See, the way we were setting up our units, we wanted cost per ounce. And remember I said, okay, if I'm doing cost per ounce, you'd set that up as a ratio. We have cost over ounces. And because it's cost over ounces, that's exactly how you do that division, is your cost divided by your ounces. Because a situation like this, unlike this first one where we ended up with 28, that was nice, right?
Exactly, yeah.
This one, we're dealing with decimal points. And your unit rates, while they're nicer as fractions, in this particular case, you know, you might be starting off setting them up as fractions. Like so. But really, you're going to end up treating those fractions as division.
Yeah. Cost.
So 275 over 22 ounces will get you whatever that amount is in dollars per ounce.
Mm-hmm. Okay, I got it. Thank you.
Always.
Okay.
And number 3, we have a grocery store is having a sale on crackers. Customer can buy 3 boxes for $5. Using that rate, what would 5 boxes cost? What was that? Hope not. That'd be a ripoff. So if you're buying 3 boxes for $5, how much is 5 boxes? Exactly. So you think, first of all, what the ratio is you're looking for. You're looking for the cost per box, right?
Yeah.
So I'm going to take that concept and I'm going to turn that into a ratio. which I'll end up using as division because the cost per box is going to be $5 for 3 boxes. So every single box would essentially cost whatever 5/3 of a dollar is, right? That's really what it ends up being.
Isn't there an easier way to do it though?
I don't know. I don't think so. Because you would do this division. Because technically you're done at 5/3, but it would work. Technically, you're done at 5/3, it would work. But you'd probably want to actually know dollar amount what you're working with. So in this case, I'm just doing 5 divided by 3 for that. And I'm rounding to the nearest penny. Now, if it's that much per box, I'm going to take that and I'm going to multiply it by however many boxes I'm working with, right? I would get $8.35. Now, technically, that does introduce a rounding error. That's a dollar sign. It's just the worst dollar sign I've ever drawn. That would technically introduce a rounding error because this number did get rounded off. Technically, we would have that. It'd actually be $8.33 if you did it strictly with fractions, which is an option. That's one way to avoid rounding errors is if we know that we're doing this math and we're going to multiply it by 5, you can leave everything in its exact form until the very end and only round at the end. And that would take care of any rounding errors you would have. Since I rounded this to the second digit, that kind of broke, you know, the 0.66666, you know, the 2/3 happening after that. Completely broke. So that's why we ended up with 835 instead of 833. Now, if you're going and buying something at the store, you better believe that they're going to round it off in a way that they make more money. So it is going to end up being the 835 probably.
By 6 boxes.
Like when I worked at GameStop, I figured out that you know, when you have to combine a percentage off and a dollar amount off, it would do the dollar amount first, then it would do the percentage, because the percentage of the smaller amount is it's a smaller dollar off, it's a smaller discount. I'd say that's how they get you, but let's face it, they get you however they want to. Okay. No, we're not doing that. Proportions. We already had 2 hours of practice so far, right? You guys probably don't want to do that. I don't want to do it. I wrote all those problems this morning. That was the effort I'm putting into them. You just embrace the fact that the next class is going to have to do them. All right, so proportions. Proportions are useful. It's 2 ratios that are equal to each other. It's saying that, hey, if you say something's proportional, that means it scales up to the same rough value, right? So the comparisons of the lengths of the shadow of a small object versus the shadow of a larger object would be proportional because they're both being cast by the sun, right? So proportion can be used in many real-world situations. An unknown value in a proportion can be solved for by cross multiplication. So in this example, a factory can manufacture 84 bicycles per day when it's at 70% capacity, how many bicycles can be produced at 100% capacity? So you would say, okay, you set that up as a ratio. You say, okay, well, 84 bicycles at 70% capacity. You would set that up, maybe one on top of the other. I have essentially bicycles over capacity in my example, 84 over 70. And then over on the right side, we have no idea how many can be produced at 100% capacity. So we just call it a variable, B for bicycle, whatever. Don't really care what it is. It could be an X because algebra, but you know, call it whatever. And then you would cross multiply to get the answer. Now, cross multiplication, I don't think we've done yet, but the idea is that you can only do it when you have a fraction equal to another fraction. I will be showing you that in a moment in examples. I love examples. And they're all word problems. Isn't that great? So the first one, we have a shadow problem. So we have an 8-foot lamppost casting a 12-foot shadow, and then it's saying that a nearby building is casting a 30-foot shadow. And we're looking for the height of the building. So the idea is that these two ratios would be proportional to each other, right? So the ratio of the height of an object would be proportional to its shadow, and that would scale over to every other object in the nearby area, right? So what I usually do is I will set up kind of like how I did on the unit rates. I always set up like a mock ratio for my units. So I might do whatever the object is over the shadow. I just set that up now so that I know that I'm able to keep everything straight later. That's how I'm keeping it straight. It's going to be the object over the shadow. Now, all of these problems, all the proportional problems are always going to be a fraction equal to another fraction. Always. Okay, so an object over its shadow, the lamppost is going to be 8 feet tall, and the shadow is 12 feet long. When it comes to the building, we don't know its height, but we know its shadow length is 30 feet. If you don't know how high it is, you can just, you know, here's the thing. A lot of people are terrified by algebra. A lot of people are terrified by numbers or letters in algebra. You've already seen me use a little bit of formulas. We've had A, B, whatever. It's literally just a stand-in for here's a number you don't know. So you can call it whatever you want. A lot of times when it's a height, I'll call it H for height. You might call it X for, hey, this is kind of the catch-all for algebra. But we're just going to use H because why not? Now, at this point, you use something called cross multiplication, which only works when you have a fraction equal to another fraction. The idea, here's the long way of doing it. You know, I like showing you the long way, why it makes sense. If you hate fractions with a passion in equations, the way to clear them would be to multiply through both sides by whatever common denominator you have. That would cancel out everything, right? Now, I don't know what the common denominator is between 12 and 30. I don't care right now. I'm just going to say, okay, whatever 12 times 30 is, good enough, whatever. If I multiplied both sides by both 12 and 30, you don't necessarily have to write this down. But if I multiplied both sides by 12 and 30, what would happen? Well, the 12s would cancel over here, and over here the 30s would cancel, right? I wouldn't have fractions anymore. I would just have whatever's here times that and whatever's here times that. Well, what just happened? This number is the only thing left multiplying by this guy. And this number is the only thing left that's being multiplied by this guy. So what has happened is we've accepted a shortcut called cross multiplication. And the shortcut is literally, hey, if I did this every single time with every single fraction equals a fraction known to man, every time it will always work out that this one is going to multiply onto that, and this one is going to multiply onto that, and I'm not going to have fractions anymore. So cross multiplication itself is a shortcut. So we end up doing, and also for the record, some teachers will tell you, oh, this one has to be on this side of the equals, this one has to be on this side of the equals. No, it doesn't. I don't care. It doesn't. If I have 2 equals h, I have h equals 2. It's the same thing. Doesn't matter. As long as this multiplies onto that, 8 times 30, we have 240. And this one multiplies onto that, 12 times h, I have 12h. There's an equals between them. I don't care if you end up with a 12h over here and a 240 over here. Doesn't matter. Means exactly the same thing. Now, at this point, all you have to do is solve for that h. So the idea with solving something like this algebraically would be to say, hey, if I'm trying to get that h alone, what's happening to it right now? It's being multiplied by 12. Okay. So I want to get rid of that 12. How am I going to get rid of it? Divide it away. You do the opposite operation. We have 12 times h. Let's divide off that 12. Because, hey, what's 12 divided by 12? 1. So it cancels. 1 over 1. 1 divided by 1 is 1, blah, blah, blah. We only have h left. Over here, 12 goes into 240. I don't know. It goes into 24 twice. So how about 2 with a 0 out of the end? That cheap? I like it. So we have 20 equals h. What the hell does that mean? The height is 20. Okay, 20 what? Well, let's look back at this. Height is the height of the building, and everything else is in feet. So the building is 20 feet tall. There's a proportion. In case you've ever wondered, you know, for instance, how we know certain distances between things that we can't, you know, run a measuring tape across or what have you, things are proportional. Okay. Let's do another. Theo wants to use a cookie recipe that makes 36 cookies, but he wants to reduce the number of cookies to 24. The recipe specifies using 2 cups of sugar. How much sugar should he use? So the way I always do these, word problem wise, is I like to kind of do like a little scratch area of putting the important bits together, right? So I know I have 30, the recipes calls for 36 cookies. I'm reducing that to 24. It's calling for 2 cups of sugar. We're reducing that to, I don't know. So what I'm going to do is I'm just going to do exactly what I did last time. I'm going to set up a little mock ratio, and I might do cookies to cups of sugar. Cookies cups. Now you might say, hey, does it matter which one's on top? The answer is no. It could have worked out either way, if I had flipped both of these fractions upside down up here, the cross multiplication still would have ended up with this exact thing. So it doesn't matter which one is on top and which one is on bottom. It matters that you keep it consistent. If I have, you know, the object over its shadow over here, I better have the object over its shadow over here. So that's why I'm setting it up this way. If I'm doing cookies over cups on one side, I better do it the same on the other one. So if 36 cookies would get 2 cups of sugar, 24 cookies would get how many cups of sugar? Now you might look at this and say, hey, that's a fraction. I can reduce that. Can I do that? Yeah. I don't know if I would, because we're gonna cross multiply, but yeah, you could. Just for the sake of doing things the same way every time, let's not. Just in case. It would actually turn into 18/1, and you could cross multiply, but you would be tempted to write that as 18, and then that would break the cross multiplication. So that's why I'm not doing it. So 36 times C is 36C, 2 times 24, 48. And then since we have 36 times C, I want to get the C alone. So I'm going to divide off that 36. C equals, I don't know. We could reduce this, right? That's a fraction. I could say 12 goes into here 4 times and into here 3 times. So I'd have 4/3. I could divide those two and get a decimal. It'd be 1.33. But if you're working with measuring cups, you're probably not going to have 1.33 cups on it, right? So this is a problem where mixed fractions would probably come in handy. 3 goes into there once, with 1 left over. 1 1/3 cups. That's something you could actually do. And that's actually a good application of when we would use mixed fractions versus decimals. You could totally get away with doing decimals. If this was a word problem, yeah, decimals is fine. If you're doing it at home in your kitchen, I would probably want to have that, right?
Wait, so where did you get the 4 and 3 from?
Because these would both reduce by 12. So 12 goes into 48 4 times, 12 goes into 36 3 times.
Okay.
Yeah. What do we think? Do we like it? How do we feel about proportions compared to the other crap? We like them? Little better? Little better. That's what I'm trying to do. I'm trying to bring us back, trying to, you know, make sure that more of you show up on 5 days from now. Okay. Let's not do those alone. Let's see. I want to do one more and move on. Yeah, I like that one. Okay. Number 3, in order to determine her pulse, June's nurse counted 18 beats per minute. Okay, not 18 beats per minute. You're gonna die at 18 beats per minute. 18 beats in 15 seconds. How many beats would she have per minute? That's how much room I'm giving myself. All right. Because I mean, we're looking for beats per minute. I bet I'm going to do beats over minutes. Right? Makes sense. Actually, let's not do beats per minute. Let's do beats over seconds. Because I'm dealing with seconds for now, right?
Wouldn't you just take the 18 and times it by 45?
Well, not by 45. You'd multiply it by 4, and that's the easy way to do it. But we're doing this with proportions, man. All right.
There's 45 seconds left in the minute.
So we don't know how many beats are happening in a minute. A minute has 60 seconds. Why did I switch that from minutes to seconds? Because I was dealing with seconds here. And if I kept it in minutes, I would have to put 15 over 60 right here. I really don't want to do complex fractions right now. Neither do you. So we're going to have to cross multiply. I'm going to get 15x is equal to, I don't know what 18 times 60 is. $1,080. And I'm going to divide it by 15. Goes in evenly to 72. Now, in terms of unit, what do I call this? Is this beats per minute? Is this beats per second? It's tricky, right?
Yeah.
Well, what was it out of? 60. Yeah. So since it would have been 72 over 60 seconds. That's the same as a minute, right?
Yeah.
And 72 is a number where you're not going to randomly die. 18, yeah, you're probably gonna die. Who? Let's see. I don't wanna. Moving on. How many slides of information do I have? 1, 2, 3, 4, 5, 6. 6 slides of information before I get to any examples. I have 11 minutes. Think I could pull that off?
Yeah. I think you can.
I think I can too. You know what? Whatever. I don't care. So this is actually not bad. It's easy. There's a lot of vocab to it, but the actual method is stupid easy, and we're running directly towards something called a factor tree. If you've ever done a factor tree in your life, that's what we're doing. So prime factorization. Factoring is the process of breaking a number or expression, whatever you got, down to smaller factors. So it's kind of like what we'd be doing in the lowest common denominator, where we're like, okay, well, what multiple can go into these? You're kind of fitting multiples together that way. Prime factorization is breaking something down as far as it'll go. It's not lowest common denominator. I was thinking of is canceling. Yeah, I'm also tired. All right. When we're canceling, you're looking at things and you're like, oh yeah, 2 goes into both of those, right? Maybe 6 goes into both of those. Prime factorization is the option of taking all your numbers, breaking them down, and saying, oh, I can look at what goes into all. It's kind of nice. It's actually very useful. So vocab wise, a prime number is a whole number greater than 1 that cannot be made by multiplying other whole numbers. It is divisible only by 1 and itself. So like 3. 3 is a prime number because what goes into 3? Nothing really, 1 and 3. 5, 7, not 9, because 9 is what? 3 times 3, right? not 10, 11, nothing else goes into 11, so it's prime, et cetera, goes on forever, right? Composite number is just. Ugh. Okay, I feel better. It's just what we call a number that's further divisible. So it's composed of multiple prime factors. Now, 1 is a weird number. It's not included in the definition of prime numbers because that would break things a lot. They have to be divisible by 2 distinct numbers, 1 and something else. 1 is only divisible by itself, so it's technically not a prime number or a composite number. It's its own weird little thing.
Is 0 a prime number?
Gonna say no. What multiplies to 0? Anything times 0. Let's not play with zeros. So here's an example, and it's kind of a crappy way to find it. You're not going to do it this way. If you're trying to break something down like 12, you would say, okay, well, what goes into 12? Well, 2 goes into there 6 times, right? And that's 6, you can break down further. You'd say, okay, well, 6 can be 2 and 3, right? So we have 2 times 2 times 3, and that's our 12, right? Writing it out that way is just painful, right? I don't care about any of these. Nope, we're not playing that. So this is actually something I do like to cover. It works great if you very clearly see what numbers go into what. Works fine. And in fact, a lot of times you'll look at a math book and it'll just assume that you can perfectly factor something just by looking at it. It'll skip all the steps in between 2 little bits. And I hate that. It's stupid. I can't look at something and be like, oh, obviously 45 goes into both of those numbers. No. So what I prefer to do is I do a factor tree, which you might have used at some point. So factor trees, you literally just start with the highest number that you got and start breaking it down. You can break it down however you want. Like this 48 here is just broken down as 8 times 6 first. And then each of those branches starts breaking down further. The 8 can be 4 times 2. The 2 is done at that point, but the 4 can be broken down as 2 times 2. Over on the other side, the 6 can be broken down as 2 times 3. So you break it down as far as it'll go, and you end up in this case with 2 times 2 times 2 times 2 times 3. So the nice thing about this method is it will work regardless of how you do it. I could have started with the 48, thrown a 2 at it, got a 24, then taken that 24 and turned it into 3 times 8. And that would be my 2 and my 3, and then I'd have an 8. 8 breaks down to 3 more 2s. Hey, look, I have 4 2s and a 3 again. So no matter how you do that, you will always end up with the prime factorization of a number. Now, I have a bunch of random examples here. I'm just going to touch on a couple of them, and then I'll let you guys free. Yes, I'm taking every moment I can. I regret nothing. Hashtag deal with it. All right. I'm going to do number 1. I'm going to do number 4. And I'm going to do number 6. And it is 8:26. Do I have enough time to do this? Oh, yeah, I do. Because these are easy, right? So 100, what goes into 100? It's 10 times 10, right? First thing you think of. Okay. 10, 10. Okay, what goes into 10? 2 and 5, right? 2 and 5? Well, same with that 10, right? 2 and 5. When it comes to writing down the prime factorization, I prefer that you write it in order of lowest to highest. You can go the other way if you want to, highest to lowest, doesn't matter. Just kind of keep it even, right? Keep it nice, keep it simple. But that's it. That's all it is.
You wouldn't add the 10, 10?
What was that?
You wouldn't add the 10s?
Nope, it's only what is at the bottom of the branches. If I've broken that down, it's no longer something we're thinking about. Yeah, so once I break down that 100, I don't care. Once I break down that 10, I don't care. At that point, it was 2 times 5 times 10. Once I break down that 10, I don't care. It's 2 times 5 times 2 times 5. And if you're ever worried about it, you've done it and you're like, I don't know if that's correct, throw that at a calculator, see if it comes up with the same number. Number 4, 78. What goes into 78? I don't know. Right? Okay, but it's even. So 2. Go over to Mr. Calculator here, 78 divided by 2, 39. Pretty sure 2 doesn't go into that. I bet a 3 though, right? 3 goes into that 13 times. Does anything go into 13? Not that I know of. 2 times 3 times 13. All right, there we go. That's not bad, right? About 132. I don't know, but it's even. 132 divided by 2, 66. First thing that comes to mind, 6 and 11. Well, 11's prime, we're good there. The 6 breaks down though. All right, everything's broken down as far as it'll go. We got a 2, 2, a 3, and an 11. It's the bottom of every branch. Questions?
Okay, so the other 2 gets added into the answer because it wasn't broken down.
This one?
Yes.
Because it's the bottom of a branch, even though it happened all the way up here, it's still, that's as far as that guy can go.
Okay, yeah.
Yeah.
Okay.
Yeah, and if it helps as you're going down, if you break something down, you can always just don't care about it anymore. Don't care, don't care. It's everything else at that point. But yeah, that's it. Covered those, what, 6, 7 slides? Might have skipped a bunch of them. Covered the concept. And yeah, we will pick up with prime factorization and figure out what horrible hells that it might lead into on Tuesday. Have a magical evening.
Bye-bye.
Goodbye, sleep well. I know you all sleep well now.
Put that back.
Bye.
Good night, everyone.
Okay, thank you.
Good night, Ben. Good night, everybody.
Rock
I'll be in
on.
class. Yeah, I'll see you like next week for sure. I'll come in to actually
Okay.
talk about it. All right, dude.
Hey,
Have a
whenever.
great weekend. Yeah.
You too.
Have a great weekend. If I have any questions, I'll message you, dude.
All right.
Later, bro.
Bye.
Did you get my message?
I don't know. I wasn't looking at my phone. You sent something?
On the chat in here.
Oh, you mean the chat that I have covered in a window? Oops.
Yeah.
If I 6 times and make it $10.
And then can you like do it that way? Break it down that way?
I mean, you could, but it's still gonna come out the same way. You're still gonna have to multiply at some point.
Okay. Yeah, I was just curious on that because I was thinking like,
Well, the nice thing about unit rates is they scale up. So conceptually, yeah, 6 boxes would be $10. 9 boxes would be $15. You can go up until you hit the point where it actually like works for you. But generally the aim is to get down to a unit rate. So you have how much 1 box is, and then you can multiply it by whatever the heck you need.
okay.
Yeah.
All right. Cool. Thank you.
Yeah.
This weekend.
Have an awesome weekend.
You too.